Chapter 21.5, that section of chapter 21, deals with recognizing graphs in terms of combining together all the knowledge we have of these various new functions we've experienced at grade A on A star, and to match these functions with unseen equations. But obviously there's no guesswork here. What we're doing is trying to match shapes that we know and recognize with equations that seem likely to fit those properties of the graphs that have been drawn in front of us. So if we look at graph A, this is question 1 by the way, on page 321, it says match each function with its graph. Well, I've got the function or equation y equals minus 2 over x, so it's essentially based upon 1 over x, isn't it? And that's called a reciprocal graph. Here we got y equals 2 sine x. Essentially we're looking for a sine x type squiggly graph like that. Here we have a cubic function, y equals x cubed minus 2, so you're looking for something that has a positive skew like that, positive arrangements rather than the negative one that does that. And here we have a quadratic function, y equals x squared minus 5x, so you're looking for something a little bit like that. Alright, so let's go. Here we have a lovely cubic function, classic shape, and it has an intercept, a y-intercept in the negative territory, so we're looking for y equals x cubed minus something, and there it is. No, where is it? There it is, there it is. So I know for sure if it's x cubed minus 2, that's the coordinate 0 minus 2. Doesn't ask us to dissect it to this level, but there it is. So this goes with y equals x cubed minus 2. Very easy. And that's C. Next one, classic reciprocal function, which is this one. So here I've got y equals minus 2 over x, and that's going to be therefore graph A. Just put little rings around them. Here, classic quadratic equation. That's going to be that one there. So y equals x squared minus 5x, and that's going to be D. And for your information, that would be the coordinate 5, 0. I could tell that because, well, I can factorize this. Let's just go into it if you want to do that. Factorizing, I get two solutions. And where y equals 0, look, I've got x equals 0 and x equals 5, because 5 minus 5 is 0. So there's your one solution, two solutions. Again, that's just revision, some old grade B stuff. But there it is, we've matched it quite happily, and without having to think, the last one's got to be y equals 2 sine x, and therefore option B. There it is. 2 sine x, what's the difference? Well, instead of the sine value peaking at 1, it's actually going to peak at 2. So that, for example, would be 90 degrees, and the sine of 90 degrees is 1. So 2 times the sine of 90 degrees would be 2 times 1, which is 2. So that's all that's about. But it still maintains the classic up-down, you know, complete sine wave. It's beautiful. So that's that one, and we're going to move on. Same thing, but probably a little bit tougher. This is question 2. Just look at the book there. Yeah, question 2. Same thing. 4 curves, 4 equations, 4 functions. So y equals x squared. Right, 3x squared minus 2x plus 1. We're looking for a quadratic down here. Y equals 3x squared minus 2x plus 1, and that y-intercept will be the coordinate 0, 1, because that tells me so. So I've matched it, and that's graph A. Y equals 3 cos x. Well, we're based on cos x, aren't we? So cos curve, a bit like the sine curve, but different. The cosine of 0 is 1, but it's 3 times the cosine of x, so 3 times 1 is 3, so that coordinate will happen to be 0 degrees 3 up, and that is the graph of y equals 3 cos x. Not that you can tell, there's no values to play with at all, it's just that you know it's a cosine curve. It starts with the cosine of 0 peaks, and then the cosine of 360 degrees will also peak at 1 as well, but it's 3 times cos x, therefore it will peak at 3 there and 3 there and minus 3 there, if you're interested. So that was graph B. Next one, y equals 3 over x, in other words based upon 1 over x, reciprocal graph, and there she is. Y equals 3 over x, and that was graph C. And without having to think at all, this is going to be option D, y equals 3 to the power of x. A lovely exponential graph. Again, I love these, the way they just suddenly take off as you increase that power more and more and more. That's going to get really big really quickly. I hate plotting them though, especially going to negative territory. You can't really plot fractions like eighths and quarters and sixteenths. It's really difficult. Doesn't matter. Appreciate the shape, and certainly that's an exponential graph. Y equals 3 to the power of x. They could have put any integer there, or even a decimal number like y equals 3.7 to the power of x if they so chose to. That's not the point. The point is you're recognizing it's an exponential function, and that's the shape that we've got. Next question. Again, I'm going to do all of these. This is question 3. Now, Anna says this is the graph of such and such. Bindia, whoever she is, says it's that. Chris says it's that. Dave says it's that. Who's right, who's wrong? Explain why each of the other students is wrong. Well, let's forget all these guys. Forget them now. What have I got here? I've got a classic cubic curve, but it's negative. So I'm looking for something that says y equals minus x to the power of 3 somewhere in the equation. It doesn't cut the y-axis in the positive direction, and it doesn't cut it in the negative direction. So there won't be a number like minus 3x plus 6 at the end, or minus 6 at the end, because the intercept on the y is 0, 0. So therefore there won't be any random number floating around. So let's just take these one at a time. Anna says it's y equals 4 minus x cubed. Let's just rewrite it. Anna's equation is therefore minus x cubed plus 4. But you know, can't be right answer, because there isn't a y-intercept of plus 4. It doesn't do this, for example, in which case that will be the point 0, 4 if Anna was right. She's wrong, because the graph passes to the point 0, 0 and not 0, 4. Alright, so I won't write these down, but I'm saying it to you now. It doesn't pass through 0, 4, it passes through 0, 0 on the y-intercept. Right, Binder says it's x cubed minus 4x. Wrong, because it is a negative x cubed type graph. It is a minus x cubed type graph or function. Alright, so here's me saying I won't write it, but I've written it. I just couldn't help myself. What about Chris? Chris says it's minus x cubed plus 4x squared, or 4x squared minus 3x minus x cubed. Could be, don't know yet. After all, Anna's one was negative x cubed and got it wrong because of the intercept. Let's look at Dave. Y equals x cubed, wrong, plus 4. Doubly wrong. He's wrong for two reasons. Number one, it's a negative x cubed type graph, and it does not pass through, I'm writing it, aren't I? And it does not pass through 0, 4. It doesn't, does it? I mean, just like Anna's one there. See, that's her 0, 4 intercept, and that's Dave's written that way around. So that's why it's wrong. It's a negative x cubed one, not a positive x cubed one. And Dave's saying it passes through 0, 4. It doesn't. It passes through 0, 0. See, the only guy who's correct is Chris. Who is correct? Answer, Chris. And I can't explain why, but it's just to say it is a negative x cubed type graph. We can't really explain this without physical values, you know, being put in and coordinates plotted. So at least I've explained why all the others is wrong. Revise. Why is Anna wrong? Although she's cited it's a negative x cubed type graph, she also says it has a y-intercept of 4, whereas in fact the graph passes through 0, 0. Why is this Bindia wrong? She made it a positive x cubed graph, but it's a negative x cubed graph. Okay, that's why she's wrong. Chris is right because he's right, because he's clever, because he's named after me. That makes him right. And Dave says that the graph is x cubed plus 4. Wrong on two grounds. It is a negative x cubed type graph, and the intercept is not 0, 4 but 0, 0. So that's that question done. I'm going to do question 4 and then stop there, because I want to save question 5 for its own little video. Now the sketch shows 4 curves PQRS, and again we've got to match them, haven't we? So what do we got here? Y equals 1.5 to the power of x. So this is an exponential or power graph. Now we know these things take off like that, alright? That is an, what do you call it now? A reciprocal graph that goes something like that. That is a power graph that goes whoosh like that. And this is another reciprocal graph that goes like that. Right, let's just take them one at a time. It's working red, I think. So I've got 2 power curves and two exponential curves, I like to call them power curves, and 2 reciprocal functions. Let's just do the reciprocals first. There's that one and there's that one. So B and C. Let's look at it very carefully. Now I've got y equals 1 over x and y equals 5 over x. Which is which? Well, these are the 2 reciprocal functions, Q and P. What they haven't done, of course, is drawn us the negative expressions of these things, and there would have been something like this and like that, perhaps. All right. So that's, if you like, the flip side of the graph in this area here. But they've not bothered with that. Do you recall that the number above the x, the numerator, if you want to call it that, the bigger that number is, the further away the graphs are from the axes. So listen, this Q graph is further away from the x and y axis than the P graph. So therefore the Q graph is going to be the one with the bigger number. So that one's going to be y equals 5 over x. Don't need 2 equals, is that silly? And the P is going to be y equals 1 over x. Alright, so P is y equals 1 over x, close to the axes, and the Q is going to be 5 over x, y equals 5 over x, which is further from the axes, and that's how you can tell them apart. Now what about these power graphs? Let's work in blue, I reckon. Right, I've got that one and that one. Now here's the question: 1.5 to the power of 1, 1.5 to the power of 2, 1.5 to the power of 3, etc. Again, you've got a calculator if you're going to play with these numbers. 3 to the power of 1, 3 to the power of 2, 3 to the power of 3. Answer: which one's going to accelerate away and take off quicker? Clearly the one with the bigger base number of 3, because if you power up a bigger number, it will get bigger quicker than if you power up the smaller number by the same amount. So for example, 1.5 squared is going to be less than 3 squared, clearly, because 1.5 is less than 3. 1.5 to the power of 4 is going to be a lot less than 3 to the power of 4. And if you want to work it out just to prove it yourself, you can. But it's logical to assume that. It's obvious in a way. So which one's taking away, which one's accelerating away quicker? Well, I've got this one that goes and rises and is called graph S. And this one, in the same space of time, takes off much further. Alright, so if x was the same value, for example, there and there, S has this value, but R has a bigger value. So which one is which? Easy. R is going to be the one that takes away quickest for the same value of x. So we've got here y equals 3 to the power of x, which leaves this other one which takes off less quickly, y equals 1.5 to the power of x. So there we are. That's the graphs all matched up, wonderfully done and excellently taught, even if I say so myself. Now question 5, I'm going to give it its own little video and then I'll be back.